here we are. I want to do everything. So pretty much every problem that we're going to do the rest of the week is just graphing everything. But I'm not just going to give you the problems like on your homework where it was a nice polynomial all multiplied out. I might give you some rational functions. I might give you polynomials in factored form. And we have to be able to work from there. Now, could you choose to multiply this all out before you did anything?
Yes.
Yes. Do we want to?
Yes.
You can. I don't really want to. But
it's gonna be a lot easier for me to derivative that.
oh, we can do product rule. It's good review for us. So remember, product rule, we do one thing at a time. So derivative of the first. So the 2 comes down. Inside stays the same. Subtract 1 from the power, so it's now to the first. Times derivative of the inside, which is just 1, so I don't need that, times the second. Plus the first. Derivative of the second is just 1. Okay, here's what I'm going to do. Before we get too crazy multiplying this all out, look, we have 2 terms, and they both have an x minus 1, right? So just because I'm trying to ultimately have this factored so I can work with it, I'm going to factor out an x minus 1. So we get x minus 1. And if we distribute and add like term, x minus 1 times 3x minus 5. Now, did I have to do it this way? No. If you wanted to multiply out the original because you didn't want to do product rule, you can. If you wanted to do this derivative and then multiply everything out and refactor, you can. You just have to get here. So at this point, can you tell me, what are my critical points? Because that's where my derivative would be 0. All right, that's the first thing I asked. Increasing, decreasing. So that's when we make a sign line for this. So smaller than 1, in between, so maybe 1.1 and bigger. So if I plug in a 0, I get a negative times a negative, which is positive. If I put in 1.1, so that would be a positive times a negative, which is negative. Put into positive times positive is positive. So we are increasing negative infinity to 1, 5/3 to infinity. Decreasing 1 to 5/3. All right. In my directions, I said local and absolute. We can't really do absolute max and min because I didn't give you endpoints. So we just need the local max and min. So if I switch from increasing to decreasing, what happens at 1? Local max. Okay. Order of pair, if I put in 1, and you're putting that into the original to get your y value, and we get out 0. Then at 5/3 we were decreasing and switched to increasing, so that's a min. Okay, so 5/3 times 2/3 squared is 4 times negative 1/3, negative 1 over, or negative 4 over 27. You guys checking me?
Yep. You know it.
Put way too much faith in me. Okay, thank you. How do I get inflection points?
This
Second derivative. Okay, I'm just going to do it from here. Okay, so my second derivative, I'm going to do product rule. So derivative of the first, derivative of x minus 1 is 1 times the second. What I simplify too.
Oh, you can do that?
If you want to multiply it out and do it from there, you can. I'm just doing the product rule. So derivative of the first times the second plus the first derivative of the second. So we get 3x minus 5 plus 3x minus 3. So it's 6x minus 8. So inflection point is when this equals 0. So we get
8/3. No.
8 over 6, which is 4 thirds. To distribute this 3.
Oh, 3 plus 3 is 6.
Usually.
Not 3.
Okay. For our inflection point to actually plot it, we do need the y value. So let's go ahead and get that order pair. Again, if you're getting the actual point, you're putting it into the original. So that would be 4 thirds minus 1. 1 third squared is 1 9. So negative 2 over 27.
Yep. Because the other denominator was 27.
So
And they were
absolutely makes sense.
They were the same denominators in both of the things. So, and 4 is smaller than 5, and 2 is bigger than 4. Negatives. So there.
Okay, so now we want to know concavity. So we're going to do a sine line here. And we're going to put it into the second derivative, the 6x minus 8. So if I put in something smaller than 4 thirds, I get a negative. Bigger than 2 thirds, pi. So this is concave down from negative infinity to 4 thirds. Concave up from 4 thirds to positive infinity. All right, everybody with me so far? Okay. Then I ask for you to draw the graph. So when you're drawing the graph, start with like your maxes and mins. Those are actual points. So we had 1, 0. And then we had 5 thirds. So that's like a 1.6 and negative 4 over 27. So just barely negative. And then inflection points we mark with an X. So 4 thirds negative 2 over 27. We know that our graph is increasing and curved downward at the beginning.
Attention please, the following is...
All right, so we're increasing, so we're going up. We know when we're going up, we have two options. It can be like this or it can be like this, but we're curved downward, so we're the second option. So it's like this. And then we hit this point, and then we're going to switch to decreasing. We're still curved downward until we get to our little X, and then we kind of curve upward. And then after this point, we remain curved upward, but we are increasing. So it should look something like that. Maybe a little prettier than mine, because I kind of had a little hiccup there. But all right. Is that one good? That really ate into our class time, but I'd really like to try to do one more problem. If we could. So, I want to do one that's got asymptotes in it. Alright, so we have 2 over x squared minus 1 over x plus 4. Vertical asymptotes are x equals what makes the bottom 0?
0.
Horizontal asymptotes. We have found those this year. Do you remember what we did?
Derivative. Sine. Limits. Limit.
So quotient is
We had to do positive and negative infinity. A lot of times we did those separate. But as long as you don't have like a piecewise or like radicals, those kinds of things, we can put them together. But you do need to show me that you're thinking about both the positive and the negative. Now remember, if you get a number over infinity, what's that turn into? 0. So this is 0 minus 0 plus 4, so we just get 4. So I have a horizontal asymptote, y equals 4.
Wait, you're gonna have to explain that again because I'm lost.
Okay. The limit as we approach infinity. So it was first semester when we were doing limits. Anytime we had a number over infinity. Remember, I used the analogy, I have 2 pizzas. Okay, and I give them to you guys. So you're each getting, I don't know, 3 pieces of pizza or whatever. And then I invite Mrs. Dyer's class in. What happens to the amount of pizza you get?
Less.
You get less. Then I invite Mrs. Keller's class in, so you get even less. And then I invite everybody in the gym in. So the amount you're getting is getting smaller and smaller. It's turning into 0.
Yeah.
So this went to 0.
Minus 0 is 4. Okay.
All right. Critical points. That's the first derivative. Now, it might be helpful to you. 2 over x squared, we could write that as 2x to the negative 2. 1 over x, that would be x to the negative 1 plus 4. So if I'm doing that derivative, you get negative 4x to the negative 3 plus x to the negative 2. So to find my critical points here, it's a little bit uglier. This is like saying negative 4 over x cubed plus 1 over x squared. And I want that to equal 0. What could you do to figure out what makes this 0?
Maybe do that thing where you multiply over the most x's.
Okay. So what happens if I take everything times x cubed? So I get negative 4 plus x equals 0. So x equals 4 is a critical point. Remember, critical points are anywhere the derivative is 0 or undefined. When is this derivative undefined?
0.
Okay, so it's basically what would make the top or the bottom 0. So we got our critical points. For increasing, decreasing, we need our sign line. So if you put in negative 1, you get a positive plus a positive, which is positive. You put in 1, you get negative 4 plus 1, which is negative. Put in a 5. That one would give us a positive again. So we are increasing negative infinity to 0 and 4 to infinity. We are decreasing from 0 to 4. Max and min. So at 0, we went from increasing to decreasing, right?
Yeah.
Which means max. What happens when you go to plug that into the original?
It probably doesn't exist.
Yeah, can you do negative 2 divided by 0 or 2 divided by 0? No. So there is no max. At 4, we went from decreasing to increasing, so that's a local min. So if you plug a 4 into the original, so we get 2 over 16.
What's 16 times 4?
31 over 8, is that right?
I'm trying to get there, but I'm still finding.
How do we get inflection points. So I'm going to do my second derivative from right here. So that's 12x to the negative 4 minus 2x to the negative 3. And we need to know what makes that 0. Can you tell me right now what has to be a critical point? 0, because it makes it undefined. And there are different ways that you might get it. We can do the same thing we did last time, multiplying by the highest power of x. We could get for a common denominator. We could try greatest common factor. Any of those will work. Let's just do what we did last time. So if I take everything times x to the 4, we get 6. So 6 and 0 are the inflection points. Okay, then for concavity, so if I put in a negative 1, it would be 12 plus 2, so that's positive. If I put in a 1, I get 12 minus 2, which is still positive. I put in a 7, I would put in negative. Now, I cannot just say we're concave up from negative infinity to 6. Why?
I'm not there yet, actually.
Okay.
Because there's an asymptote.
There's an asymptote, so we do have to break it up. Say negative infinity to 0, union 0 to 6. Then we are concave down from 6 to infinity. So this problem had absolutely everything, as much as I could throw at you. It had the rational function, we had asymptotes, all the other stuff. So now when I go to graph it, my max and min, let's see, there was no max. If I plot my asymptotes, we had a vertical at 0, horizontal at 4. We had local min at 4. 31 over 8 is not quite 4. Inflection point. We need an actual or pair. 0 was an asymptote. But when my x is 6, if you plug a 6 into the original, 35 over 9. And this is really going to be kind of hard to tell from my graph. I didn't do a very good job of this. But, so we had our min here, and our inflection point is even closer to the asymptote than that. Okay, so my graph, we have to be increasing and curved upward to start. So if my graph is increasing and curved upward, we know how it behaves around asymptotes. It's getting closer and closer to them. That means it has to look like this. Then we are still going to be curved upward until we get to our little x here. But now my graph is going to decrease until I get to 4. So it's curved upward, but decreasing. And then after 4, we switch back to increasing. So it's going to increase, it's going to stay curved upward. Oh, my graph is really hard to tell. And then, so it's increasing and then just kind of leveling off there. you might be starting to see why it's really, really hard for me to make all these numbers nice and pretty. Because I need all the x values for first and second derivative come out nicely, and the y's. That's a lot. So we are going to be practicing this for the next couple days. Today I'm going to give you a few problems out of the textbook. They're not all doing everything. I think only one of them is graphing everything, or a lot of them are just finding pieces of information. Then Wednesday and Thursday we will be practicing the graphing. So I have nothing new left to teach. It's just practicing putting all this together. So we have 4 problems.